So I wanted to take a second and talk a little bit about Riemann sums and area under the curve and things like that. And I briefly did this in class the other day, but I'm not sure I did it very clear. So let's kind of think of an example where we have a function, it goes like this. We want to know the area from 2 to, let's say, 5, and the function is the square root of x. And I don't know how, yet. I don't have a tool to find out exactly the area underneath there. So the best thing that we say is we can do is we can approximate it, and we're going to approximate the area by splitting it up into rectangles. And in this case, I'm going to split it up into 1, 2, 3, 4, 5, 6 equal width rectangles. They don't always have to be equal width, but most of the time in our examples you'll see them. So I'm going to call the left boundary A and the right boundary B, and n is going to be the number of rectangles that I have. And so the first thing that I wanted to show you is that if I do my left endpoint approximation, I get 1/2 times, and I'm going to take this plus this plus this plus this plus this plus this. So what is that? This is going to be f of 2 plus f of 2.5 plus f of, well, that's going to be a lot of writing, so I'm just going to dot dot dot. And my last rectangle that I'm going to have, by the way, I know I'm going up 1/2 because it's a total width of 3, and I'm dividing it up into 6 rectangles, so that's going to be 1/2 of a step for each one. In the left endpoint rectangles, my last one is going to be 1/2 of a spot before the right edge, which is 5. If I did my right endpoint rectangles, it would look kind of the same in a lot of cases, except it's like every rectangle is getting pushed over by 1, and so I have a lot of the stuff that's in the middle is going to be the same. My first rectangle is going to be f of 2.5, my second is going to be f of 3, and my last one is going to be f of 5. So if you look at what's happening, everything that's in the middle gets matched up with another one. What the left endpoint has that the right endpoint doesn't have is f of 2, and what the right endpoint has that the left endpoint doesn't have is f of 5. So now think about what would happen if I just, to pass the time during these days of the pandemic, wanted to add up the left and the right endpoint approximations. What would I have? I would have f of 2 plus f of 2, well, so I would have 2f of 2.5, so I'd have 2f of 2.5 plus 2f of 3, and I'd have 2 of everything up to 4.5, and then I'd only have 1 f of 5. And then if I wanted to just get an average of those two figures, because we know a lot of times we know that our left endpoint is going to be either an under or an overestimate, and our right endpoint is going to be an under or an overestimate. And in this case, since the function is increasing, my left endpoint estimate is an underestimate, and my right endpoint estimate is an overestimate. So if I wanted to say, well, let me just take the average of those two, I I'm not quite sure if that's an over or an underestimate, but I know that it may be a little bit more accurate than just the left or the right endpoint estimate by itself. And I just remembered to turn the set of headphones that was already on my ears on, so maybe you can hear my mic better. The other way that we talked about in the last section estimating these is the trapezoid estimate. And if you think, what's the trapezoid estimate going to be? Well, it's going to be f of 2 plus f of 2.5 divided by 2 plus f of 2.5 plus f of 3 divided by 2, dot, dot, dot. And the last one's going to be f of 4.5 plus f of 5 divided by 2. And if you look at what's happening here, you're going to have 1 f of 2, you're going to have 1 f of 5, and everything that's in the middle, you're going to have 2 of. And so if I wanted to write this another way, I could write it as 1/2 of f of 2 plus 2 f of 2.5 plus 2 f of 4.5 plus f of 5. And so what I just hope that I convinced you of is that the trapezoid estimate is the average of the left and the right endpoints. And so some of you, if you have programs on your calculator that can find the left or the right endpoint by itself, sometimes it's easier than doing the trapezoid calculation to just find the average of the two. And I think it helps your intuition to know that the average is the same. The average of the left and the right endpoint is the same as the trapezoidal estimate. I think there still is a good question of what type of function will a trapezoid be an overestimate for, and what type of function will a trapezoid be an underestimate for. And I'm not going to answer that, but I think that's a good one to think about because it's not as easy as increasing and decreasing. But this Riemann sums is a topic that builds quickly. It's now, I think, still review from the end of your pre-calculus class. But let's just say that we want a general formula, and I have a function f of x is equal to x squared, and I want to go from 2 and I want to go to 6. A is going to equal 2, b is going to equal 6, and I'm going to make a lot of rectangles. I'm going to make n equal to 12, and I'm just going to draw, there's something like 12 rectangles there, and then I want to think, what is our formulas going to look like? And I'm going to do let's say the left endpoint rectangle first is going to be, well, calculate the width of the total space first, which is 4, and then the width of 4 divided up into 12 rectangles is going to be 4 divided by 12, or 1/3. And then I would have to multiply it by f of 2 plus f of 2 1/3. And the last one would be 5 2/3. And if I do my right, it's going to be fairly similar. It's going to be f of 2 1/3, f of 2 2/3. My last one is going to be f of 6. Okay. What is important is that we figure out a way to write this using the capital sigma, the Greek letter that you often see on fraternities when you go to college, which are things that you generally should stay away from. These jokes work better when I'm teaching an actual class and have an audience. So the formula with the sigma is going to need a counter, and I need a letter for the counter, and the counter that we usually use is I. And when I think about what is going on with this, I want the counter to go up by 1/3 each time. And where is it going to start? It's going to start at 2, and it's going to go up by 1/3 I. And so for the left endpoint, it's going to go I equals 0 up to 11. And for the right endpoint, it's going to be the same kind of thing, but instead of starting at 0 and going to 11, it's going to start at 1 and go to 12. And if you sort of think what's going to happen, when I is 0, this thing's going to be 0, which means my first rectangle is going to be f of 2. In the right endpoint, I starts at 1. So when I is 1, this is going to be 1. My first rectangle is going to be f of 2 and a third. My last rectangle is going to be 12. So when I put 12 in there, I'm going to have 12 thirds, which is 4. 2 plus 4 gives me f of 6. That's what I want. When I put 11 in here, that's going to give me 2 plus 11 thirds I, which is f of 5 and 2 thirds. So let's say we want a general formula for f of x is equal to x squared plus 3x plus 2 for a is equal to 4 and b is equal to 5 and n is equal to 11. And my left endpoint formula is going to be, I'm just going to sort of like picture in my head now, I'm not even going to draw it, what this formula is going to look like. Well, I know that the width of each rectangle is going to be 1/11. I know that for my left endpoint, I'm going to need to go from 0 to 10. For my right, I'm going to go from 1 to 11. And it's going to be, so x squared, so I need to start at 4. So it's going to be 4 plus 1 over 11th I squared plus, this is a tricky one because it's got two x's in the formula, plus 3 times 4 plus 1 over 11 I plus 2. And my right is going to be the same exact thing. 4 plus 1 over 11I squared plus 3 times 4 plus 1 over 11I plus 2. And this would be our formula. And this 1 over 11 right here, I want to give this a name. I'm going to call it delta x. And you notice that it appears twice in this formula. So delta x is going to be the amount that x is changing. It's the amount x is going up by each time. And it also represents the width. Remember, we're calculating the area. For each one of those i's, we're calculating the area of a rectangle. And the height of the rectangle is what that function is giving you. The width is what delta x is going to give you. So delta x is width of rectangle. And eventually we'll get so sick of writing the triangle, we're just going to start writing it as dx, but we're not there yet. Okay, so let's go even a little bit more abstract, and let's say that I want to know the general formula for f of x is equal to f of x, a is equal to a, b is equal to b, and n is equal to n. What's my left and what's my right going to look like? Okay, so for my left, it's going to be the sum as I goes from 0 to n minus 1 of the width, which I'm just going to call delta x, times the height. Well, I need to start at a, and I need to go up by delta x every single time I counts up by 1. And for my right, it's going to be I is equal to 1 to n of delta x times f of a plus delta xi. And it's also important that you can understand what is delta x. Well, delta x is going to be b minus a divided by n. So you should be able to recognize this formula whether it has delta x in there or whether it has this b minus a. It kind of gets confusing whenever all of those arrows. B minus a over n.